Okay, this class is on neural network. So there will be two portions of this neural network. The first portion will be talking about R, and the second portion we're talking about Python using Keras. So neural network. Now, first we want to compare neural network with regression with this decision tree. And if you look at the strength and the weaknesses, and neural network have high tolerance on complexity or data like unstructured data and high tolerance to noisy data, etc. But the weakness is that it actually act as a black box. And of course, we have learned logistic regression and decision tree that the logistic regression is quite good when there's a linear regression, despite you do not assume that. And if that's the two between the two classification, there's a clear line, there's a clear linear relationship. And but the problem is that it actually, because of assumption on the linear relationship, it actually assume that all the error this uh, is always in a random form, which indeed it is not. Okay, so these are some things that we look into the comparison. And of course, a more detailed one. So actually, for non-linearity and complex relationship, decision tree is always better. So in general, decision tree actually have a better data structured. For structured data, actually can perform better than regression. So same thing, decision tree and logistic regression. Now neural network is similar to logistic regression because the way they look at how the algorithm works is actually quite similar. And neural network. So later we'll go into more detail on the algorithm for neural network. So first, it actually started with how humans think, and it actually emulate that. So a neuron is basically just a memory if there's multi-layer, and then it's just a addition of all the sigmoid that make the neuron is just a number. You know, it can be 0.5, 0.7, the weight can be 0.8, 0.9. And just to let you know that usually we normalize it to between 0 to 1 using sigmoid function. Later we'll go through more detail on that. So a perceptron example. So example, your input is 2 and 1, and the weight is 0.5 and 0.3. Then you have a bias of -1. So with that, you will have 2 times 0.5, which is the weight, and then after that followed by this and then followed by this 1 times the 0.3, which is the weight. Then everything you minus 1 as a bias. So this is a perceptron. So a typical neuron is a perceptron evolving from here. So you have 2 hidden layers. So every single dot is a perceptron here. So this is a perceptron, and okay, so this is a perceptron here. So you just multiply this by the weight, then you add every one of them, there will be the weight here. And hidden layer, so you can have multiple hidden layer. So think about it, a hidden layer, each one of these will be one linear regression, right? So because you add all the coefficient times the input, right? So it's like x1, x2, x3, x4, and this is your coefficient, like beta 1, beta 2, beta 3, beta 4. Then you add all them together. So think about it is many linear regression, many linear regression. So network structure. So you actually have an input layer, and you can have multiple hidden layer. So it seems like it's like a linear programming, because linear programming has many linear uh, uh, regression to make a linear programming. And the outer layer is always one, and input layer is one, and the weight is the one that link between the two neurons. So this example is cheese acceptance taste test. So it's quite easy, a simple one. You have the fat score, you have the salt score, and the acceptance. Apparently, if this is high, then people like it, right? This is a tasteless, so people don't like it. Of course, today things are changing as well. Huh? Okay, so this is a high taste, and people like it. So if you look at this salt thing, so this is the fat, this is the input layer, this is salt, this is a two-dimension here, and you have the weight. Say this is 1 3, and this is 1 4, this is 1 5, and this is the hidden layer neuron. You have 3 4 5, and this is the bias, and then you have the weight, and this is another bias, and this will be your output, whether it's 0 or 1. So that's a function. Okay, so I would say that the is linear, because you actually multiply by the weight, multiply by the input, right? But the activation function is a non-linear, so usually we use sigmoid model. So the scale is either 0 to 1 or -1 to 1, or z-score, which is -2 to 2. Usually we don't go to until -3. But the -1 to 1 we can use 10, and 0 to 1 can use sigmoid. So if you look at this now, so initial weight can be anything that is a random number. So the bias can be 0.3, 0.2, 0.05, sorry, -0.3. So this is as good as the beta 0, which is the y-intercept. Okay, so in a linear regression, so we always compare this in a linear regression, and this is 0.05, 0.01, -0.01. So now we do the first row, 0.2, 0.9. So if you still remember, our first row of data is 0.2, 0.9. So now assuming that we put in 0.2, 0.9 as our first input. So this is 0.2, 0.9 when go in, multiply by all the weight. Okay, and then after that, you have this summation. Then after that, you have the output, which is 0.43. So at this stage, then this is 0.51, this is 0.51. You multiply this further, then with the bias, you have 0.0506, 0.506. So 0.506, but your desired outcome is 1. So most likely you have to add the weight to make it closer to 1. But you may not want to add everything. You probably add by a learning rate. And your learning rate can be 1%, 2%, 3%. So the activation function is using this sigmoid, which is 1 plus e to the power negative something, right? So sigmoid will translate the numbers to between 0 to 1. And if you look at the sigmoid at this layer, 0.05 times 0.2 plus 0.01 times 0.9, which is referring to 0.05 times 0.2, 0.01 times 0.9, correct? So it's referring to this. Then this is minus 0.3, is referring to this. So the answer should be 0.43, which is referring to this. So of course you can repeat the process to get 0.51 and 0.51. And you can repeat the process to get 0.506. So you can do that. So the outer layer is the same thing. So you repeat the whole process, you will get 0.506. And the output node, so if this is 0.506, then you know that it's different from the one that you desire, which is 1. So the difference is 0.494, right? So this is the final output, the 0.506, and then so you have to do backward propagation. You have to update the weight. Okay. So this is the whole thing is called one epoch. So you have to increase all the weight to make it closer to one. Okay. But bear in mind there's only one first row of data. Subsequently, you have multiple rows of data again. So this is 0.56 is only one of them. And this acceptance. So this is the final weight, and after multiple epoch, and the weight is just try and error, right? So because of that, your learning rate must be low enough. And this is another example that I like to do it on the second part of the recording.